Good afternoon, everyone. I'm Shotade Olusegun. In today's video, I want us to dissect the mechanism of mass decay of weak nuclear force. Well, mass decay of weak nuclear force is so mysterious, and people have been scientists have been trying to decipher uh, that mystery. They want to demystify. They have been working so hard to demystify that mystery of nuclear fusion. But in this video, we're going to actually dive deep into reality of that. We want to get what is or things that are responsible for the nuclear, what we know as nuclear fission, which is decaying of mass. Well, it is not well, basically, just as we have a nuclear fission, we as well have nuclear fusion. And so that the nuclear fusion is the merging of deuterium to tritium. Those two are two isotopes of hydrogen. Well, there is one thing about these isotopes of hydrogen that misses one. There are, basically, when you look at deuterium, that is when you have additional neutron in the nucleus of hydrogen. So when you have that, you have deuterium. But when you now have additional, when one neutron is added to that, you have tritium. But one thing about tritium is it then becomes unstable. Well, that is telling us that there is boundary at the edge of let me say hydrogen domain. So it's more or less like every atom has its own boundary. So they have, all atoms have their edge boundaries. And so we're going to see that when we look at the merging of deuterium to tritium, we see that the boundary which we have in form of repulsive force is being overridden. You understand, to emerge higher and more massive element, which is helium. So basically, this phenomenon, we could see that in the time energy wave model, the diagram that we have here. We're going to actually dissect that to know and to see the boundaries. So the boundaries at the edge of every atom is so essential, because that repulsive force at the edge of every atom has to be overpowered in order for us to have the more massive element. And then we can see that once that happens, then the parial identity, which is in this case hydrogen, is being transformed into another identity, which is helium. So that is how we can move from, and I think that we actually lead to formation and transformation or formation of various or many elements that we have in the universe. You understand? So now let's look at we're going to use this diagram on the board to actually explain, or to visually explain the phenomenon. And we have that phenomenon of nuclear fission in the gravitational phase of time energy wave model. And so we have the nuclear fusion in the expanding phase or expansion phase of time energy wave model. So how is that in any way related to time and energy? So let's dive deep into it. Here we have energy wave traveling inversely to time wave. Well, if you have been watching my video, you'll be conversant with this time energy wave model. That is just the visual representation of the universe, the reality of universe. So now you can see that in this expansion phase we have nuclear fusion. Now the reason this is so is that, I said that the margin of of deuterium and tritium will give us higher mass, will give us higher element, which is helium. Well, when we look at it, by having higher or bigger mass or bigger element, that will invariably expand time energy wave model, and that is why we have nuclear fusion in this phase. So now the contracting phase, which is gravitational phase, we have nuclear fission. Now nuclear fission, we know that has to do with decaying of mass, and well, all this, this decaying of mass is being mediated by weak nuclear force, and it is so mysterious. But now what we have right here is that the decaying of mass is synonymous to what we have at classical level or at classical realm, where we have a very huge sun, big sun, decaying into neutron star and later decays into singularity of the future phase, which is known as a black hole. So now the decaying mechanism is to negate mass worth of an element to the point where it gets so light. But as we are having that decomposition to light formation, then we have another thing which is known as mass energy formation, and energy formation, or rather let me say energy concentration. So energy concentration is what we have as energy density. And so in this momentum phase where we have energy being higher than time, we have energy concentration. So here we have energy density instead of having mass worth. Here we have mass worth, and here we have energy density. So now, by understanding the true nature of time, and then by understanding the relationship of energy to time, then we're able to have clear picture of what nuclear fission is, and also what the nuclear fusion is. And so we can actually relate the two to the past phase or the future phase or the expansion phase or the gravitational phase respectively. So now that is that about nuclear fusion. But the thing is, how do we now get to the point where we have the nuclear fusion? When we look at this fixed point, we have fixed point right here, and this is the minimum fixed point. It is known as a stable fixed point. The fixed point we have up here, the fixed point we have up right here, that is known as unstable fixed point. Now, by the time we have a trajectory of energy, like particles approaching the low energy state, and when it reaches the lowest point, for this particle, for it to be elevated or to travel to higher level, probably maybe as we have it first level, second level, third level, as we have it in atom level of excitation. So before this particle can actually be elevated, there must be an additional energy. Well, we know that when atom absorbs energy from outside, then that will elevate particle to higher state. So basically, the additional energy that is needed, we actually have it from the higher dimension by using formula of everything, and in this case we use electron mass. And so electron mass worth, which is the original one, we got that from the outside the system, which is outside the system of time energy wave model. And so once that is pumped inside the system, which is in this case so tiny space, then that will accelerate the particle towards the singularity of the future. And by having increased energy relative, or by having increased energy relative to time scaling, which is low time scaling or narrow time scaling, then that will actually cause mass decay. So now what we have here is the beginning of mass decay, because the mass worth of electron we have at low energy state that is being pumped into narrow space that will cause that acceleration, that mass worth is so huge than the space, and as a result the mass worth will be unstable, and that will cause quick or instant, almost instant decay. And that radiation generated will actually accelerate particle towards the future singularity. So we can now say that same thing is applicable to decaying mechanism of either the oldest sun that we may have in the universe, or a big or super sun that we have, that we explode into supernovae or supernova or whatever it is. So now when you look at it, in the case of the sun, it means that the sun has grown. It has grown past the assigned space, the assigned space. And once it is so bigger than the space that is accommodating it, it will become unstable, and that will result to that supernova. And that supernova will decompose that very big sun into neutron star. So the neutron star, it's more or less like a suspension phase, or a suspension phase to the singularity, because the electron will be so compressed into the nucleus of the sun, and so electron will be in the nucleus, and as a result of that, the size in the nucleus is bigger than what the nucleus can also accommodate. That will make the nucleus to be unstable, and that will result into further decay into singularity. And once that happens, then gravity will crunch, or will compress, or will compact what is it called, the neutron star into singularity. Because as you can see in our gravitational phase here, we have two forces compressing towards the singularity. We have the force of time and the force of energy, and so that will be more than what the neutron star can actually withstand, because neutron star is more or less like having a repulsive force. Because when you have, neutron and proton, they have a kind of repulsive force, and once they are in close range, the repulsive force will be more intense, and that way is more or less like preparing a ground for neutron star not to be compressed into singularity. But the contraction of time to energy is so intense than what neutron star can withstand, or rather even what facilitates the decaying further is the electron being in the nucleus of the neutron star, because being there will generate additional more mass. Even the repulsive force itself, its mass on its own, with what we already have in the nucleus, and that will make the nucleus to be so unstable. And once it explodes or implode, as the case may be, it will be totally compressed into the singularity of the future, which is black hole. So that is the mechanism of weak, or let me say it is the mechanism of mass decay of weak nuclear force. And so we're able to have that based on the novel discovery, which is by using the formula of everything and then using time energy wave model. So I believe this video is quite informative. If you like the video for real, like it by clicking the like button. Don't hesitate to share with your friend. We want this new knowledge, new discovery to, we want it to spread quickly and wide enough for people to, have the knowledge of it, so as to advance our science and technology as it ought to be. So please share this video with your friends as many times as possible. Then don't forget to subscribe to this channel so as to be notified for the subsequent videos. Then there will be more interesting videos on this channel. Then another thing is it's a novel discovery. So I'm going to actually put the link to my research publication in the description below, so anybody can get the published article or published issue publication to you know to work out what we have on the board. Thank you. God bless you.